Hello everyone. The second part of Optics 2 lectures that we will be going through, we'll be considering spherical mirrors. For that we need to consider a transparent sphere, and I can consider two sections from it, that is AB and A prime B prime. And the section AB is silvered on the outer side of its curve, so that the inner side becomes a reflecting. Obviously, it's a hollow sphere, so the inside has nothing, it's completely hollow. And the section A prime B prime is silvered on the inner side such that the outer curved surface is a reflecting one. So we have two kinds of reflecting surfaces over here. These are mirrors which are formed out of silvering the sections of spheres of different of a certain radii, and hence they are spherical mirrors. So it's not necessary that we get such mirrors by cutting away sections of spheres. There are machines which are capable of which have been employed to obtain the exact shape and kind of mirrors one might be looking for. So we can go back to the figure again, and here AB is from silvered from the inside, so its outer surface is reflecting one, and it is called a convex mirror, spherical mirror, which is a convex mirror. Whereas A prime B prime is silvered on the outside, so that its inner surface is a reflecting one, and such a type of spherical mirror is a concave mirror. Okay, concave, you can consider the cave-like structure with the hollow uh, part being the reflecting one. So that is how we can consider these mirrors, spherical mirrors. Some terms that we can usually associate with them are as follows. That is, the first one is center of curvature. Now, the center of the sphere of which the mirror that has been considered, okay, here the center is at O, and AB and A prime B prime have their center of curvature at the point O. So the center of the sphere of which the mirror forms a part is known as the center of curvature. The second term is the principal axis, or in many cases is also called as optic axis. Now the principal axis is an imaginary line that passes through the point O, that is the center of curvature, and divides the mirror into two equal halves. So the mirror is divided into two equal halves with the principal axis passing through its center. And the next one is the pole, and it is the point on the mirror through which the principal axis passes towards the center, such that AP is equal to PB in the convex mirror, or A prime P prime is equal to P prime B prime in the concave mirror. Okay, so that is so P and P prime, that is the pole of the respective mirrors that has been considered, right? And the next term is the radius of curvature, that is usually denoted by capital R. So the radius of curvature is the radius of the sphere of which the mirror is a part, and here OP is equal to OP prime, because we have considered the same sphere for both the mirrors, and both will have obviously the same radius of curvature, that is capital R. Okay, so and the final term that we can come across, or the fifth term, final term is ahead. So the fifth term is aperture, and it is the length of the given mirror. It can be taken as a straight line or in terms of angle. Now in case of straight lines, I have considered two dotted lines from A to B, or from A prime to B prime, and these are known as the length here gives the linear aperture. But if we can calculate them in terms of angle, then the angle AOB and the A prime O and B prime, that is the angular aperture. So the next let's focus on the focus of the mirror, of a given mirror. So here I have considered concave mirror, and parallel rays parallel to the principal axis have been considered, and they are incident, and the normal here is obviously the normal passes through the center of curvature of the given mirror. Now the reflected ray, they will meet at a point which is called as the focus, and the point lies on the principal axis denoted by capital F. And here the focus is real as the rays are actually meeting. So the reflected rays here are actually meeting. They can be obtained on screen. So that is what we mean by the term real, means the image for anything can be obtained on the screen. Now consider this convex mirror. Now in case of convex mirror, with the outer curved surface being a reflecting one, so the incident light rays uh, considered parallel to the principal axis, they are reflected, and the reflected light rays will obviously diverge, while the normals that are considered at the point of incidence, they will meet at the center of curvature. The reflected light rays are divergent, so they are produced backward along their reflected path to meet at a point on the principal axis, which gives the focus. Now this producing the reflected light rays which are not actually meeting, so that they can form an image, so this gives the focus, and this focus obviously, as you can know, is not real, it is a virtual focus. Okay, so the rays actually do not meet, and therefore it cannot be obtained on screen. The distance between the pole and the focus of a mirror along the principal axis is called as the focal length, usually denoted by the letter small f. Okay, so this was all about focus, and a plane mirror can be considered to be a very small section of a very big given spherical mirror. A very small section that I have considered by the curly braces that you can see over there, it's the relatively bigger curve, and the lines are almost straight. So as the mirrors considered are very big, their radii also must be very big in terms of the objects placed in front of them. So their focal lengths are undefined or taken to be infinite, because we cannot really measure their focal lengths in our real life. We do not have the instrument every time, so the focal lengths are relatively very big. Now let us obtain the relation between the radius of curvature and the focal length. Okay, now so for a plane mirror that we considered in the previous case, that has the focal length to be nearly tending to infinity. Now here I have considered the same cases of reflection, while the naming in each case, the incident light ray strikes a given mirror. On the left we have a concave mirror, and on the right we have a convex mirror, and it strikes the plane mirror at the point M, and it is reflected towards, or appears to be reflecting from the focus, reflecting towards the focus in concave and appears to be reflecting from the focus in the convex. As the angle of incidence in each case is I, considering that the incident ray is parallel to the principal axis, angle MOF in the triangle OMF is also equal to the angle I. That is quite clear from the geometry of the figure if you observe closely. And also the angle FMO, that will be equal to the angle R, that is the angle of reflection. And so triangle OMF is an isosceles triangle where OF is equal to FM, as I is equal to R. Usually the mirrors are less in curvature, and the rays rendered parallelly are close to the principal axis, and hence are called as paraxial rays. Now these paraxial rays, because of them, so the isosceles triangle, in that case we get the line FM to be nearly equal to FP because of the paraxial consideration, and FP is the focal length, that is F, and so OF is also nearly equal to FP, that is the focal length. Now the radius of curvature, as you can see from the figure, R is equal to OP, which is equal to OF plus FP, which is equal to F plus F, which is equal to 2F. So R is equal to 2F, or the focal length F is equal to R by 2. So that is the relation between the focal length F, small f, and the radius of curvature R. That will be all for this video. Thank you for watching.